I am going to do a shorter lecture this time, just so I can cover the material in your chapter. What is it? Chapter 7. Okay, so I am currently sharing. Oops, I skipped down to another slide, but this is a slideshow, and it has a few slides on it, but the entire slideshow actually includes material from the next chapter. So I haven't uploaded this PowerPoint. Instead, what I did is I included the important slides in your module. So for your module this week, you're just going to have the important slides, and then this PowerPoint is for another class. But I'm just going to use it to keep on track. So what we're going to do this week is basically a study on fossils. And your book, your chapter 7, is based all on fossils this week. So I think it's a little bit shorter than I usually do, because in other classes, usually the section combines fossils and also other sections of primates to primate fossils. But in this case, it's just fossils. It doesn't include primate fossils, which we'll cover next week. So we'll do a whole complete separate lecture on that. All right, so all of you, I'm sure, have heard of fossils, but not many understand what fossils are. And so your chapter goes into the different types of fossils. And this particular picture right here probably looks familiar. It is the icon that's on Canvas for this course. So this is a fossil, and I chose this specific fossil because it has a few interesting things going for it. So first of all, this is a 2 million year old fossil that was found in Georgia. And when I say Georgia, it's the country of Georgia in Central Asia, next to Azerbaijan, Armenia, not the state in the United States. So this is a country where this fossil was found. It's also sometimes considered part of Eastern Europe, even though geographically it's more Asia. But it is interesting because of what this fossil is. So this fossil, it has been determined to be of Homo erectus. So Homo erectus is a previous species to ours, which is Homo sapiens. So Homo erectus existed before we ever evolved. We are more than likely descendants of Homo erectus. But I'm going to get into how we can't 100% determine that because of some restrictions or limitations that we have with fossils. So this is a 2 million year old Homo erectus fossil found in Georgia, and it was found in about 2004. So it's been already 20 years. And this fossil is really interesting because, first of all, as you can see, this picture was taken before it was completely extracted from its place in the earth. So this is found in situ. In situ means in its location, just like that. And it is completely intact. And that is very rare to find, especially for a 2 million year old fossil. Usually when they find fossils, they're fragmented, they've been crushed to some degree, they have to, or due to erosion or other forces, they've been spread out or scattered. And so when paleoanthropologists or archaeologists are looking at fossils, a lot of times what they have to do is gather up all the pieces, and then in the lab later on, they take them back and have to kind of try to fit them together like a 3D puzzle. And sometimes pieces are missing. But in this case, this one is almost completely intact. The mandible as well, even though the mandible is the lower part of the jaw. It's probably down below here. That was also found. And the other thing that's really interesting about this fossil is that it has a head shape that is a little bit different compared to most Homo erectus that they knew of at that time that existed. So I'll talk a little bit more about that because there is an article that I've linked in the modules. All right, so that's the story on this particular fossil. There's actually more to the story, and I'll get into that when we get to the article. All right, so what is a fossil? There are different types of examples of what fossils are, but the basic definition that I'm going to give you is a fossil is basically a mineralized cast. So, a mineralized cast of what was once organic material. And that organic material can be bone or antler. There's another term that is discussed in your book, which is taphonomy. And taphonomy has been defined as the study of how fossils are formed or produced. Your book has a broader definition, and it says that taphonomy is the study of what happens to remains after we die, which is a good definition as well. It's a little bit broader. It's not just looking at fossils, but just overall what happens to the body. And it gives a few examples. So now I want to show you just one thing that I like to do. Okay. Okay, so I've now put up a picture or my paint screen, and this will be a little bit difficult since I usually do this on the whiteboard and I'm not good at doing this on my computer, but I like to show what's meant by taphonomy. So when people think of fossils, I gave you the definition, and I'm going to show you what that definition means. But I think most people don't realize just how special fossils are sometimes. You have to have the conditions just right for a fossil to form. Because if you think about it, so when someone dies, we'll make this a person, kind of a person. That's a leg, and these are arms. And again, I'm doing this on my mouse pad, so I don't have the best control of what I'm drawing here. So when someone died in the past, obviously now people get embalmed and buried and put in, uh, hermetically sealed coffins, sort of. But in the past, when we died back 10,000 or however thousand plus years ago, um, actually some people were buried. We have found, going back and looking even at Neanderthals, we have found Neanderthal burials. So people started burying their dead a long time ago. But let's say going back past Neanderthals into Homo erectus, we don't have evidence that they buried anyone. So when someone died back then, you just died and were left on the ground, right? As any other animal. So this doesn't have to be a human, it can be any type of um, animal that dies in the wild. And what ends up happening? You're left there exposed to the elements, to rain, sun, and depending on how hot it is, that can actually increase bacterial proliferation, how much bacteria there is in the environment, and how much bacteria will feed off of you. And the more bacteria there is, the faster the decay process is for the soft tissue. So the soft tissue goes first. And this is assuming no other animals are gnawing on you, because that happens as well. Animals, they can bite through flesh and bone and get to the bone marrow. That happens typically too. And so you might have animals, not just gnawing on your flesh, but through trying to get through your bone, trying to get through your skull into your brain. Sorry, I know this is very vivid, but this is what happens. And so in a lot of cases, animal or human remains, or hominin remains would have been chewed up, chomped up by other animals and bacteria, you know, long before any fossilization can occur. Fossilization takes time. So if you die out in the elements like that, chances are your body won't be preserved as a fossil because it'll be consumed long before any fossilization can happen. So again, fossilization takes special circumstances, and it takes your body being protected, or the organism's remains being protected for it to form. So in cases where fossilization forms, a lot of times what's had to happen is a quick burial of some kind. So if, let's say, this remain were buried under a landslide that occurred quickly, that's one way. And so you have a quick covering of the remains, and it remains undisturbed, at least from larger animals that can consume it quickly, or pulverize the bone. It still can be exposed to bacteria, of course, especially if it's a very hot and humid environment. And so fossilization still probably wouldn't occur then, even if it's covered. So it has to be just right. It has to be cool enough. It has to be in an environment where bacteria can't proliferate. And so let's say those conditions are met. one condition that's been found to be really great for fossils have been cave sites. So caves are cooler, usually. They're protected from the elements. You do have some water seepage, but for the most part, caves are a great area where people have found many, many fossils, paleoanthropologists and archaeologists. So as, let's say, you're in a cave or you get buried, and you're buried under multiple levels of sediment over the years, what ends up happening is the soft tissue goes first. That is consumed first by any bacteria remaining in the soil. And then you have this bone here that's left. The harder tissue takes longer for it to be consumed. So it will get consumed little by little. But in the meantime, what's happening is in this layer of compressed dirt or soil, uh, you have this bone, and the bone is deteriorating little by little. And what's happening is in those hollows where the bone, let's say this is a skull, it's like an area where bone is starting to decay away. In these hollows, you have some moisture seepage from the surrounding soil that gets in, and what's left is the water or moisture is depositing hard types of minerals like calcium, or can be iron, can be magnesium, can be other types of minerals that flow through the soil. And so those harder minerals are getting deposited in these hollows left by decaying bone. And so here's some more bone that's gone away, and then the mineral deposits replace it. And they're replacing all these hollows. And so they're kind of forming, this replacement of bone in all these areas. But it's no longer bone. These are mineral deposits. And, over enough time, this bone will recede and you have mineral replacing it. And so once that happens, it's considered a fossil. So fossil, again, is the mineralized cast of what was once bone or organic material. So this is all mineral deposits that I'm showing, and it'll be in the shape of a skull of, whatever the bone was there. And it doesn't just happen on the skull, but happens all over the skeletal body. And then it's a fossil. Now, for fossilization to occur, it can take thousands of years. In some cases, when we look back at Neanderthals, for example, Neanderthals died out about 30,000 years ago. There are some cases where not all of their body is actually fossilized. Not enough time had passed, even in 30,000 years. So you have part of their body fossilized and part of their body that still retains some bone material, believe it or not, organic material. And it is on this bone material that we've been able to extract DNA. You cannot extract DNA once full fossilization has occurred, only if you have some of the bones still preserved. And that is why when you get older than Neanderthal, so Homo erectus, you can't conduct any DNA analysis. That is the one big limitation, is the fact that we can't extract DNA from older fossils, only if you have some bone or organic material still remaining. And that is why we actually have the full genome, the full genetic code for Neanderthals. It's because they died out recently enough, believe it or not, at 30,000 years, that some remains actually are preserved as organic. They didn't completely fossilize yet. So we couldn't actually, in theory, clone a Neanderthal, but not Homo erectus. We don't have the DNA for it. It died out too long ago. So Homo erectus died out about 1.5 million years ago. And so they're too old. All of their remains are completely fossilized, and we cannot extract DNA, which is a bit of a limitation because we can't see how closely related we are. For example, if we take our DNA, Homo sapien DNA, and compare it to Homo erectus, we don't have any Homo erectus DNA. So we can't look at how closely related if we have some type of ancestry with Homo erectus, but we can compare Neanderthals. And we do see that Neanderthals and humans do have a shared ancestry in some populations. So we did not evolve from Neanderthals, and that's actually something that was corrected after we got Neanderthal DNA. We thought we were the direct descendants of Neanderthals, but it turns out that no, Neanderthals actually left Africa before Homo sapiens did, and we evolved separately from them. So they evolved in Europe and the Middle East, Neanderthals, and Homo sapiens evolved in Africa. But we do have a bit of a shared ancestry because when we finally left Africa, Neanderthals were still around in Europe, and we actually coexisted with them for a few thousand years, and we reproduced with them. And we still see that legacy today. There are some populations that have that shared Neanderthal DNA. And so it's really amazing and it's really cool. But this is, in a nutshell, how fossils are formed through this replacement of organic bone by mineral deposits. All right, so let's switch back to slides. Okay. One thing I just wanted to say again regarding taphonomy and how fossils are formed is that, again, there have to be special conditions for fossils to form. And so, for example, sharks, we don't have a lot of fossils for sharks because most of their um, body is made out of cartilage, which is too soft typically to form fossils. And so we just have jaw and teeth for a lot of ancient fossils or shark, fossils, shark species. So you have to have the right bone composition. You have to die in the right environment. We don't have a lot of fossils for New World monkeys, for example. We have to rely on monkeys in other areas because New World monkeys died in really hot tropical environments when or where there was a lot of bacterial proliferation, and so the bacteria consumed those remains far too soon before they could form fossils. And so those are some limitations as well on top of the DNA that I mentioned. Okay, so this is just a couple of questions that I posed to my class. Is the fossil record nearly complete with only one missing link? So when I was going to school, I don't know if this is even talked about, but there was one big misconception about the human line or our family fossil line, which was that we had all the species that we'd ever learn, could know about, except we had one link that was notoriously missing that would connect our line to ape line. And it was just one species. And so that was called the missing link. So is that true? Well, it is not true because there could be dozens of missing links that we'll never know, because if you never form a fossil, if that species never forms one, example, of a specimen, a fossil specimen that we have to know that it existed, where's the proof that it existed? We'll never know that that species existed. So there could be dozens of missing links in our fossil lineage for humans that, tracing back to going back to apes that we'll never know about. And those will always remain a mystery. They'll be lost to time. So there are probably many species that we'll never ever know about. They just, died out and there weren't the perfect conditions to form a fossil, and so we'll never know about them. And the ones we do know about, though, are really special, and they do tell us quite a bit. But there could be obviously many more that we'll never know about. Can DNA be extracted by fossils? The answer to that is depends on how long ago the specimen died. And if it's fully fossilized, no, it cannot. We cannot extract any DNA. It's only if it's been dead for less than 100,000 years that maybe there's a chance of finding some remain, some organic remain, and that's the only way we can ever extract DNA is if there's any organic material still left over. If it's completely fossilized and there's no organic material, then no, you cannot extract DNA from non-organic minerals. That is one big limitation because when you can't figure out the DNA of different fossils that you're finding, you won't 100% ever know just how genetically similar they are. So you kind of have to, well, I'm going to say guess, but guess isn't the best word because they do have, some science. They use different types of measurements and formulas that they have agreed upon, but a lot of it is visuals. So they are limited to visual interpretation, and there is some room for differences of opinion. Now, some paleoanthropologists, when they look at a certain species and fossil, and they'll maybe think that it belongs in this one species, but someone else will say, no, 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 it has a few features that are kind of indeterminate, and I think we need to be careful and we need to put it in this other category. And that happens a lot. So, especially if you have features that are indeterminate, in other words, they can overlap with others. That happens. In this particular link, okay, I'm not going to be able to open it, I don't think, right now from the slides, but definitely look at this link. It's a CNN link, and it talks about that fossil that I just mentioned, the one from your Canvas icon. This particular fossil is one of 5 that was found in that site in Georgia, and it just so happened that this particular guy had, I think it's a male, had the lowest or smallest skull size of the other 4. The smallest of all the 5, of him included. And what's interesting is uh, there's this idea that if this one had been found by himself, they possibly would not have categorized this specimen as Homo erectus because his skull size is a lot smaller than what is considered typical size for a Homo erectus skull. But because of the fact that he was found in context with other skulls that are very typically Homo erectus, they believe he had to have been part of the same species, just, had this variation of a smaller head size, a skull size. And that is the interesting thing with science when you can't extract DNA is what's up, you have a lot that could be up for interpretation. So some paleoanthropologists might have put him in a separate species category just based on that smaller skull size and made a whole new species up for him based on this, where others may have determined no, could still looks pretty much like a Homo erectus, but because of the fact that it was found with 4 others that are very much Homo erectus looking, they determined that he must be Homo erectus. But just goes to show that you can have a lot of interpretation that that can be very different for different scientists. And this little skull kind of shows that. So that's what this article is all about. Just how that one skull showed that there are some limitations, big limitations still in paleoanthropology, and that how interpretation can, um, differ very strongly, we'll say, between different scientists. And it kind of calls into question the other species that we have found where it's been determined that it's a new species. Maybe, in fact, it's not a new species. Maybe, in fact, it's part of an already well-known species, just maybe one that had some type of maybe a pathology or just a slight variation that made it look slightly different, but it's in fact the same species. So it brings up some interesting questions. Okay, now I want to get into dating techniques. So you have to be careful with this term, dating techniques. We're not talking about Tinder dating or anything like that, Bumble or anything having to do with reproduction. So whenever you see the word dating, don't confuse it with reproductive strategies. This is a big source of confusion sometimes for some students. When we're talking about dating, in science, in this class, it's referring to numerical or non-numerical dating. Basically, how do we determine how old an object is? That is what's meant by dating. Okay, there are 2 huge camps or 2 big categories for dating techniques on how we determine the age of an object. One is relative dating techniques, and the other one is chronometric, also called numerical. So a relative dating technique would be one where you cannot determine the actual numerical number. So I'm kind of repeating myself, the actual number. You can't calculate the number with that technique. You can just determine if it's younger or older. It's a relative dating system. So the opposite would be chronometric, and this one you can. In this technique, you can determine a numerical age. So those are the 2 big categories you need to understand. You need to understand that these are the 2 major categories. Now, there are different specific techniques that you find under each of these broad terms. So I'm going to give you some examples of relative dating techniques, and you'll also have a couple of examples of chronometric dating techniques. And these are also mentioned in your book. You have to know that those are the two big camps, so the two big categories. All right, so let's start with the first one, which is the relative dating techniques. So your book talks about, let's see really quick. Let's take a look in your book. I have it open already. This is your chapter 7. So chapter 7 is understanding fossils. And there's a lot of good information that I'll go over. And let me show you where it talks about this. Okay, let's go down here. Okay, so this section, I know this book, this version at least does not have any page numbers, so it's hard for me to direct you to page number. I'm about, I don't know, a third of the way scroll down. That's as specific as I can get. But this is a section where your book talks about relative dating techniques. So the first one that I had that you saw there on that slide, and the one that's mentioned right here, is stratigraphy. It's also called lithostratigraphy in some cases. That's why I had it like that in the slide. So stratigraphy is basically the idea that when you're talking about sediments that are laid down, so remember I talked about that landslide that buried that person, and that's how it would be protected. So as more and more sediments get deposited, that person gets pushed down to the bottom of the layers. And so the oldest layer is towards the bottom, and this is referred to as also as the law of superposition. So if we look here, the oldest layer is the most bottom layer. Okay, the bottommost layer. This is the oldest one. We don't know exactly how old this layer is. We'd have to triangulate this with a chronometric technique, and I'll explain that a little bit more. But basically, from looking at this, so here you have what look like arrowheads. So these arrowheads are in a layer that is lower than, I don't know, this basket weaving. And so this would be an older um, layer right here. We don't exactly know how much older, but however old this layer is, it is older than this layer that came on top of it, that got deposited on top of it because of the law of superposition. And it is much older than, say, these buttons right here, this bottle, and this license plate, ring, etc. So we're not even looking at the material, what the material is. We're just looking at its position within these layers. Okay, so that is stratigraphy. It is relative dating based on its placement in these sedimentary deposits, with the idea that the oldest deposits or the older deposits are buried farther down, and the more recent deposits are closer to the surface. And that is it. Okay, so the next one that I had on the slide is biostratigraphy. So a biostratigraphy is a little bit difficult to define, and sometimes the definitions are really long, but basically biostratigraphy is the combination of stratigraphy and forensics. So that is biostratigraphy. So let's go back to the slide. I think I have it. Combines forensics and stratigraphy. All right, so let me see if I'll go back to, let's see, for example, okay, so I came back to here to paint, and I just want to show you how biostratigraphy could look really quick. Let me erase this guy. Okay, so for biostratigraphy is when you combine forensics and stratigraphy. But let's say, okay, I'm going to draw layers again, like what you saw in your book. And let's say in this particular layer, we've excavated down, and we're in this layer, and we're trying to determine the date of, I don't know, like some type of, uh, what could we say? Let's say a new type of skull, like a bunny skull. Looks like a human. I don't know. Let's just say this is a bunny. Again, the ears would not fossilize because it's cartilage. But let's say we find a new species of some kind of animal. I just drew this really quick, a bunny. And let's say the bunny happens to be buried in a layer with a very well documented species that we know of deer or something. I'm trying to draw antlers. It's actually going a little better than I thought. It looked like a radio antenna, but that's fine. Okay. All right. So let's say this bunny fossil is a bit new to us. We're excavating this, but then we find this guy as well in the same layer. It can actually be in a layer above or below too, but I just made it easier. So he's in the same layer. And this particular fossil is of a deer species that's very well known. And because he has been found in other areas where we can use chronometric techniques, specifically one where we can use potassium argon, which I'll talk about. That is a chronometric technique where we can actually determine the actual number of years. Um, we actually know that this species does not live um, any more recently than, we'll say, 5,000 years ago. So 5,000 years ago, this individual died out. So we determine that this object, because we have never found this species um, in any other area um, less than 5,000 years ago, that this species had to have also, in this same area, in this area now we're looking at with the rabbit, has to be between 5,000 years and however, long ago that we've started finding this species or dating this species to exist. So let's say that we know that the range that this animal lived in terms of dates would be between, um, let's see if I can type right here, 30K. This is how you write it, 30,000. I'm trying to do cursive because it's really hard on this mouse. So 30,000 years ago to 5K. K stands for thousand. 5,000. Wow, this is really difficult. Years ago. So this is the time frame for existence for this particular species, 30,000 years ago to 5,000 years ago. And so you triangulate. So this particular area, this sediment cannot be chronometrically dated. It's not the right material. You need specific volcanic material, and this material is not it. So what you can determine is, okay, so this particular rabbit must have also lived between this time period of some kind. So if this particular skull was found up here, and then this must be older than 5,000 years, right? So this is a more recent level. So this must be older than 5,000 years. But in this case, we found it in the same actual sediment. So it has to be still older than 5,000 years, but between 30 to 5,000 years. So you're triangulating. You are using forensics to match this particular species to, examples that we have of well-known deer species of this specific deer species, and we know that this species has lived between 30 to 5,000 years ago, and so we make the same determination for this one. So that's biostratigraphy. The next one, let me show you. Also relative, so we're still in relative dating techniques. All of this is relative. The next one is cultural dating. Fluorine dating is pretty simple. It's just determining the relative age based on fluorine levels. So if you have one object that had fluorine type of mineral that you find in soils, and it seeps into the mineral of the fossil as well. And the older the fossil is, the more fluorine it's absorbed. So if you do a basic fluorine analysis on one fossil and find that it has more fluorine than in another fossil and more or less the same site, you can determine that the one that has more fluorine was buried earlier or it's older. And that's basically it for fluorine dating. Cultural dating combines archaeology and stratigraphy. So cultural dating is similar to um, the biostratigraphy, but now it's using a cultural object. So let me show you that real quick. Okay. So for example, here, instead of this deer, let's say we have, I don't know. Let's say we find a cultural object, and this cultural object can be a tablet with writing on it, cuneiform, right? Uh, there, it's supposed to be some type of early writing system. Okay, so the earliest writing systems date to close to about 10,000 years ago. We don't have any writing that we have found before that. It could be possible that there is some writing style before that, but we've never found any. So that would then um, make this or put this bunny at something more recent than 10,000 years ago. So this bunny must have been buried um, less than 10,000 years ago because it is buried with a cultural object made by humans, as far as we know. No alien species, as far as we know, made this. But some humans, one human species, it must have been Homo sapiens. Human society made this writing system, and we know that writing didn't really go beyond about 10,000, 12,000 years ago. So this bunny must be younger than that based on this cultural object. Now, let's say instead of this early form of writing, we have, I don't know, an iPhone. I'm really horrible with iPhones because I've never had one. What are we on, 15? iPhone 10, the 10 came out a while ago. I don't know. I really don't know iPhones. Let's say an iPhone 6. So there's an iPhone 6. I don't exactly even know when this thing came out. But this is an iPhone 6. I don't even know if an iPhone 6 actually exists, but let's say it did. It came out in 2012. So these upper layers probably wouldn't have existed, and this bunny can be no more recent, um, or no older, I should say, than 2012. So this bunny must have been buried pretty recently. So this bunny has to be more recent, has to be younger than 2012 and 6 years ago. Wait, well, how old is how long ago? What year is this? 9 years ago. Or 11. Did I say 2012? 11 years ago. So this bunny can be no older than 11 years. So it was buried very recently. And because of this cultural object. Okay, so that's how that's determined. All right, so that is all relative dating strategies, or dating techniques, I should say. Dating strategy kind of means something different. Okay, now for numerical dating techniques. Um, this is actually very, I didn't have the rest of my slide here. Oh well. Okay, so numerical dating techniques, I have two that are the most common that your book also goes on about. So you have K/AR. K is the atomic symbol for potassium. AR is argon. So it's called potassium argon dating. Sometimes it's abbreviated as just this K/AR, meaning potassium argon. Also, you can sometimes see it written as radiopotassium dating. So when I was talking about earlier of that a deer skull that was maybe found, I was giving the scenario, maybe it was found in other places where you can numerically date it with a different type of soil, specifically volcanic soil. I was specifically thinking of potassium argon dating. So potassium argon dating is a great dating strategy, but it has limitations. It can only be used where there's volcanic material present. So any type of igneous rock, like you know, anything that's volcanic, so ash, um, oh, what's that type of rock? The pumice, for example, is stone. Obsidian, those are volcanic types of stone. It could be used on those types of volcanic rock. Okay. However, the other limitation, it's limited to time too. So with potassium argon, you can't measure, calculate age on objects that were very recently buried. So recently, I mean younger than 10,000 years ago. So you can date objects that were buried over 10,000 years ago. So 10,000, sorry, I keep saying 10, it's 100, not 10, 100. My slide is right. It's 100,000 years ago. 10,000 would be very, very, very recent in geologic terms. 100,000 years ago, still sort of recent, but 100,000 years ago or older is what the object has to have been buried in, or at the time has to have been over 100,000 years ago. So it can actually date objects between 100,000 years to the beginning of Earth, which is 4.6 billion years ago. All right. So for example, you're probably thinking, well, how can it measure objects embedded in volcanic stone? If there's a volcanic eruption, wouldn't it have been basically pulverized or burned up? That's a good question if you were thinking that. When objects are buried in a volcanic material where they're still preserved, they weren't burned up, it's usually volcanic ash. So there was some ash layer that fell or some landslide, and it wasn't hot enough for that object to have been consumed or incinerated. And we can find the fossil embedded within that volcanic ash, and we can directly date that volcanic ash. Again, it has to be older than 100,000 years. One thing I'm going to show you are footsteps that were actually made in volcanic ash over 3 million years ago, and they were able to be tested. That ash layer was tested. Lucy was buried in volcanic material, for example, and so they were able to easily test the volcanic material around her, the volcanic ash layers around her, and that's how they were able to find her exact age. So we have been lucky in finding some objects or trace objects that can be dated with potassium argon. The other important dating technique that's pretty well known is called radiocarbon. Radiocarbon, also called C14 dating, I think you do it, carbon-14 dating, can only be done, it has limitations as well, on organic material. So you can test the organic material itself. So let's say you have bone that was buried. You can test it. However, it's limited to only 50,000 years ago. You can't go beyond 50,000 years ago. So that object, whether it has organic material, I mean, it has to have organic material to be radiocarbon dated. They can't be too old. So it can't be older than 50,000 years ago. So let's say Lucy, she was buried about 3.5 million years ago, 3.2 million years ago. She has no organic material left. She's too old. But let's say in theory there was organic material still there. Again, it wouldn't have happened, but it's well beyond 50,000 years ago. So even if you have organic material and it's just a bit older, it's starting to get more and more inaccurate. And you actually have a lower limit too. You can't date material accurately below the 1950s. So anything more recently than the 1950s cannot be accurately dated with radiocarbon anymore. And that has to do with the nuclear proliferation and all the testing that they did that actually skewed the radiometric decay to some degree. And so anything that's more recent than 1950s, when they were doing all that atomic testing, is considered inaccurate. So it's only between this range of time that you can conduct radiocarbon dating. Okay, between 1950s and 50,000 years ago. So other materials that can actually be used for numerical dating, one important one is dendrochronology, also known as tree ring dating. Okay. This slide right here, it's also in the module. This is just showing how potassium argon dating works. Your book talks about it. It's called radiometric decay. So radiometric decay is a type of numerical dating technique. It relies on unstable isotopes, so isotopes that are decaying. So what happens is when you have a volcanic explosion, remember potassium argon dates the chemical composition of volcanic material. When there's an explosion, you have the volcanic material that is 100% potassium. So at the point of explosion, this is showing the point of explosion. We'll say right here, the volcanic material is just starting to cool. You're going to have 100% potassium. Now, little by little, that potassium is going to decay into argon. It takes a long time. So after how long? You can see it. 1.3 billion years, half of the material, half of the potassium is going to convert to argon. Now, what some people might think is, okay, so the half-life is 1.3 billion years for the potassium argon decay. Now, so some people might think, okay, in another 1.3 billion years, then you're going to have all of the potassium, right? So it took, 1.3 for half of it to become potassium. So the other half is going to take it 1.3 billion years more. So 2.6 to become completely argon. So this should be completely argon, but it's not. So what happens is after another 1.3 billion years, a half of that half becomes argon, not of the total of what's remaining. So instead of it being completely argon, you have now a quarter that is left of potassium and 3/4 that's argon. And then after another 1.3 billion years, you have a half of this remaining amount, half of this quarter is then converted into argon. So then you have an eighth left of potassium, and then 7/8 that are argon. And then after another 1.3 billion years, half of this remaining amount of the eighth converts to argon. So 1/16 then is left as potassium, and then 15/16 is argon, and so on and so forth. However, now you're getting into theoretical numbers because the Earth is only 4.6 billion years, so now we're at 5.2, so this is actually older than the age of the Earth. But as you can see, it decays very slowly, and it's half of the remaining amount that gets converted always. Okay, let's go to your book really quick. I just want to go over a couple things. 1 second. Okay, so back at your book. Here are the different types of dating techniques. So you have relative dating. Again, here are the specific dating techniques for relative dating. So stratigraphy, biostratigraphy, cultural dating. It might have there's fluorine dating that I mentioned. So read up on those. And then the chronometric dating techniques start here. And it explains a bit about radioactive material and radiometric decay and the isotopes. And it shows you carbon dating here and how it works with this picture right here. So carbon-14, which is what carbon dating is based on, I explained that, right, potassium decays into argon. Well, carbon-14 actually decays into nitrogen-14 right there, if you can see it, and it explains how this process works in this picture. So make sure you look at that. And here it talks about other chronometric dating techniques that I didn't get into, but you should look at those as well. I just discussed the most popular ones. This is dendrochronology, the tree ring dating, and how that works. It talks about how drought and wet seasons can affect the width of the rings. Okay. Oh, this is actually really interesting. When you have pole reversals, the geomagnetic poles have shifted in the past, and they've been able to track that. And so they can actually look at the orientation of certain metallic materials in objects as they've been buried, and they can determine more or less the direction of the poles at the time of burial, and then give a rough estimate as to when that object was buried. Okay, so definitely read up on the rest of this. One thing I wanted to talk about was here at the very beginning. It talks about this scientist named Mary Anning. I just wanted to mention her really quickly because when we were talking chapter 2 of all those scientists, it was mainly just men. But Mary Anning was actually very instrumental to the study of fossils, and that's why they start with her. And she was excluded from scientific communities, so she wasn't able to formally present a lot of her findings in a formal context. I trying to remember. I believe some people had to actually present it for her. She wasn't able to attend, so she didn't get a lot of recognition. But her work is pretty important. She found some important fossils, such as Plesiosaurus, and it talks about that here. And so definitely read up on a little bit of her life and this um, poem or tongue twister is actually based on her. So pretty interesting. So Mary Anning is an important scientist, early Victorian, well, actually even pre-Victorian, Edwardian or Regency, I should say, Regency scientist, earlier than Edwardian. Okay. Um, that's Mary Anning. And then your book also talks about different types of fossils. Actually, that's below here. One thing I want to talk to you about is the geologic time periods. So this is the geologic time scale. We're going to be talking about this more in the next chapter. But time periods are broken up into different lengths of times, and they're categorized as, for example, eons, eras, periods, and epochs. And MA is millions of years. And so we're actually in this period right here, Quaternary period. We're in the Cenozoic area and uh, Phanerozoic eon. And the current epoch that we're in is the Holocene. That started about 11,000 years ago, if you can read that right there. So we're currently in the Holocene, and some people are saying that we're entering a new epoch. I don't think it's been formally named, but this is the current epoch. When we talk about Neanderthals, you're going to hear me talk about the Pleistocene. The Pleistocene ended again about 11,000 years ago, and the Pleistocene was marked by um, ice ages and glacial periods. And this is actually important because it um, affected the evolution of Neanderthals that were living in these very cold climates in Europe. And so their body structures are very much adapted for these really cold periods that were present during the Pleistocene. And then we're going to talk about a few of these periods like the Miocene, Eocene, Paleocene, Oligocene, because this is actually all connected to um, early primate evolution. Okay, all right, so there's that. And it talks about Pangea and the huge landmass that was at the beginning of Earth before all of the different plates started moving and the continents start shifting into what are now their current positions. They were one large landmass. And you can read a bit about that. I just want to kind of walk you through the book. Here it talks about taphonomy and, oh, bog bodies are interesting. You can definitely look up bog bodies. They're actually really cool. It's an interesting way that bodies were preserved in peat because there was no oxygen or very, very little oxygen in the area. Okay, so lead up on those and then, oh, see the ice mummy. And anyway, I just want to walk you through this part and I want to show you here where it talks about plants or types of fossils. So you have different types of fossils such as petrified wood, and human animal remains get fossilized, and it talks a little bit about Lucy. You have Amber. Your book is quick to point out that the scenario that was brought up in Jurassic Park would not have been able to happen. Although it is interesting, it was based on that mosquito that was buried in the amber or embedded in the amber, and that would not have been able to happen. Okay, I want to bring up this one. This one is actually close to home. This is talking about asphalt. Instead of tar, it's actually asphalt that bubbles up from the La Brea tar pits in LA. And this is a very local site where millions of different fossils have been found buried or suspended in asphalt, typically called or and incorrectly called tar, but it's asphalt are two different materials. And just read up on this is actually pretty cool. If you've never been, it's an amazing site. I've been a few times. They found a lot of different fossils that are were preserved in the LA basin between 40 and 11,000 years ago, 40,000 to 11,000 years ago. So this is a really cool local site that was brought up in your book, and I think it's really cool. Okay, and then just read up on this. So I talked about volcanic rock or igneous rock, and then trace fossils. Oh, one thing I want to say about the trace fossil. So a trace fossil is where impressions are made, and you can get a sense of what was there. You don't actually have the material, but you have the impression of the material. So one big, really important trace fossil that we'll talk about is the Laetoli footprints. So these are footprints that were made about 3 point something million years ago in Eastern Africa, Tanzania. It doesn't say the date, but they're about over 3 million years ago. And because of the date or time frame, they actually think they were made by Lucy's species. They're footprints. And this is actually not the best picture of these footprints. I thought I had them on my slides, but I don't. I think I'll have to show them to you on a separate slide in another week. But there are two sets of footprints. So they think it's a man and a woman walking together, maybe an adult and a younger adolescent or child. And because of the footprints, they know they were walking bipedally and they were walking side by side. And they think they were made by Lucy and Lucy's species, or someone in Lucy's species, not Lucy specifically. They have found many different fossils apart from Lucy, just so you know, for Lucy's species. But these footprints were made on volcanic ash, and so they were able to test them with potassium argon dating techniques. So it's really cool. And we still have those preserved, and they can tell a lot about how the species at least walked, where they were walking, which is really cool. And coprolites, make sure you read on coprolites. These are actually pretty interesting. I didn't know about this thing called a Pusium that has a collection of coprolites. Um, Okay, I think that's it. There was one example of a cold case where they used some forensic techniques. I think it was on the um, cenote and Naya. That's somewhere in your book. It's in this chapter, though. A Native American girl. Oh, it's here. Cold case Naya. So this girl that fell into a cenote about 11,000, yeah, some 11,000 years ago that she lived. So it's an interesting case. And they were able to make some determinations on how she died and how she lived based on studying her remains, which is really cool. So it's a very old cold case, but they were able to extract her DNA. They looked in her bones and could make determinations on what she ate and how she probably died. So they think that she died from a large fall and she had injury on her pelvis that indicated that. Okay, so that'll be it for this particular week. If you have any questions, please let me know. All right, have a great week. Bye.